Welcome back, everyone. In today's video, I'm going to teach you a basic summary of quantum physics, and more importantly, how it ties into what I'm always saying, that the inner reality creates the outer reality. And this is based on the fundamental quantum principle that observer affects the observed. Now let's get started. So today, like I said, quantum physics and the basics. This is some actual science for how we create our own reality. And it's not just me, some guy on YouTube telling you about metaphysical stuff. There are many PhDs in physics and PhDs in other sciences that have come to the same conclusion. Typically, and it's funny, when you really start to dig deep into this kind of material about how the fundamental nature of the reality in the universe, you can look to all the different sciences, not all of them, but like a lot of them, especially in like psychology and in physics. And if you look at some of their PhDs who have been studying this information for quite a long time and you read some of their books, they usually all come to the very same conclusion, maybe worded a little differently, but it's like, the universe either isn't real until we observe it, that the thinking entity, that who we believe we are as a personality, as an ego, is false. It doesn't exist. It's just a thought. You as an individual entity and thinking entity is just a thought. You constantly in the back. The very first thought that you have that goes on a loop is I. You're continuing every moment to reinforce the fact that you are real. And it's kind of weird, it's kind of like, for those that know and for those that don't, it's like you really can't know that intellectually. You have to experience it, you have to be it. Psychedelics can bring you to that realization, but also intense study into these kinds of things. But that's a side note. I think we'll make another video about that, about the nature of consciousness. But in any case, in all of my videos, I keep saying how quantum physics supports this and I give some basic information. But for those of you who may be wondering or curious about more, I wanted to give you guys some more information about, just how crazy quantum physics is and how most physicists want to sweep it under the rug. They want to be like, quantum physics creates a lot of paradoxes if you try to look at it through the lens of classical physics. And if you try to look at it through the lens of everything being made of matter and energy versus everything being made of conscious awareness. And the paradoxes are resolved, at least according to Amit Goswami's theory. He's a PhD in physics, and this book is where I got a lot of this information from, and I highly recommend this book. I started reading it. I was waiting for my car to get worked on at the shop, and I had like 3 hours to kill sitting in the lobby. And I pulled my Kindle out on my phone, and I'm like, I forgot completely I bought this book like, years ago. So I saw this book, it caught my eye, and I started reading it, and I couldn't put it down. I mean, in the 3 hours I was reading there, I must have read like, I don't know, a quarter of the book. It's a big book. It was like 70 or 80 pages I read through. And it was just fascinating, the theory that he posits and how he thinks that the theory of the universe being self-aware, that essentially consciousness, not energy, is the all-pervasive force throughout the universe. And if you switch your view from energy to consciousness as the basic building block of the universe, that it actually resolves all paradoxes between classical and quantum physics, together. Whereas if energy is the thing, then there's paradoxes that exist, because energy cannot be created nor destroyed. And he explains it better than me. That's why he's got the PhD in physics and I don't. But anyway, I wanted to bring out some of the basics of quantum physics that he lays out and then tie it back into how we do create our reality, how observer directly affects observe. And the micro is reflected throughout the macro because that's what the macro is built of, the micro. But let's get started. So when we talk about quantum physics, we have to understand that physics is now split into two camps. We have our classical Newtonian physics. That's things like Newton's laws of motion. That's things like being able to throw a ball. And if we know where the ball starts and we know how much force is applied to it and we know all the variables, then we can calculate exactly where that ball will be through its entire arc, how it'll bounce, and we can tell you, if we knew everything and we had a big enough computer, exactly to the micrometer where that ball would stop. And it's the same way we landed on the moon. We had to calculate every single variable and all the data, all the forces, all of the weights, all the masses, all the gravities to nail landing that spacecraft on the moon. But with classical Newtonian physics, you can do that. Newtonian physics states if we know every single element of the equation, we can predict exactly where something's going to be. Now, and that's reflected throughout the macro, throughout the larger world. Well, as we began to discover things like the atom, electrons, neutrons, we started to go deeper, quarks, all that good stuff. we landed in the realm of quantum physics, and quantum physics is quite frankly just insane. And it's like the old adage is anyone who claims they understand quantum physics doesn't, you know? And so and this is even at like PhD level physicist, you know? So that's why this is just a very simple overview that, you know, Amit Goswami kind of helped us out with this summary here. But in the quantum world, we can't do that. We cannot predict what's going to happen in the quantum world because fundamentally, we don't know where the particle starts, nor do we know what energy it currently holds as far as like its velocity, what direction and force it has. Why? Because quantum objects are not at a single place. So the wave property says a quantum object can be at more than one place at the same time. It actually is a wave. It's a wave. Instead of being a single particle, it's a wave. Until we observe it as such, it stays as a wave. But when we choose to observe it as a particle, it actually, in the collapse theory, well, not theory, we've observed it. The quantum object does not manifest in a single space-time location, right? So right now, it's just this, you know, ambiguous amorphous wave. Now, when we choose to observe it as a particle is when it will solidify right here. Right now, it's right here, you know, X, Y, Z, this is where it is, and this is where its position is. And then when we stop observing it, it goes back to this being this ethereal wave. And the best we can do when it's a wave is have a probability. We can predict probabilistically, statistically, well, there's a 30% chance that when I observe it, it'll be here. There's a 50% chance that when I observe it, it'll be here. There's a 5% chance when I observe it, it'll be 5 miles down the road. And I'm not kidding. But the farther away from the locality it is when you're looking to actually manifest it, the probabilities drop off dramatically, you know. So it will be probabilistically where we are at. You know, and you can examine the way they predict this is they look at the wave. They look at the quantum wave. And they look at where more and more of the energy waves are overlapping and where the amplitudes of the waves are higher. And typically that's more likely where something's going to manifest when we observe it. But until then, that one electron is this wave that's in this entire space. You know what I mean? And it's fascinating. So because a quantum object, we don't know where it is right now, we cannot accurately predict where it will be later. We just can't because we don't have its starting conditions, A, and we don't really, quite frankly, understand how it moves because quantum objects jump. Quantum objects do not move in a straight line. So they don't move linearly through space. So imagine in classic Newtonian physics, right? I'm holding this dry erase marker and now I am applying a force. First of all, I'm resisting gravity, so we are balanced right now. I'm holding this equally against gravity, so it's not going down or up. You know, if I was pushing more, it would start going up. Well, even if I toss this, you see how it arced and it went through space and time linearly until it landed in my hand. Yeah? Well, quantum objects don't do that. Quantum objects pop in and out of reality. So the electron might be here. This is the electron here. And now, it's not going to move. It just pops over here. There is no moving in the linear space between the two objects. There is no travel. The object is quite literally here one moment and here the next. There is no traveling linearly through space. It just seemingly pops out of existence. We can no longer observe it. And then it pops into existence over here. Somehow, we don't know, and this is why quantum physics is crazy. We have no idea. Scientists have no idea does it travel in some other dimension we can't observe? You know, does it quite literally become unmanifested and then remanifest? We don't know. So the wave property, I want to rehash here. The quantum object can be at more than one place at the same time. And it does not manifest, and that's my word, it does not manifest in a single space-time location as a particle until we choose to observe it. And this right here is the crux. In the quantum reality, we have observed as scientists, we have learned, observer affects observed. So much so that there is even the abstraction that were there ever no observers, there would be no universe because quantum physics requires an observer. It requires someone to observe, some external entity to observe for this thing to manifest as it is, which is one of the reasons why I think Amit Goswami believes that consciousness must be, the aware consciousness must be the pervasive force of the universe, because otherwise, if there was never an observer, there'd be no universe. And if you had to wait until like humans or animals or whatever evolved, right? Well, it's impossible. It's a paradox. You know, the universe can't exist without the observer, and the observer can't exist without the universe. So in theory, this universe shouldn't exist unless we don't understand. Maybe the first observer was God, and God is the entity that observes everything. I don't know. I mean, that's, again, we don't know the answer to that. And another neat part of quantum physics is entanglement, or as Einstein called it, spooky action at a distance. So the idea with entanglement is certain particles can be, we can force particles to be entangled, right? Meaning they are entangled with each other, or sometimes they're just naturally entangled. And what happens is any changes that we make to this particle, particle A over here, near instantaneously show up in particle B. I know, it's crazy. Like quantum, we look at this particle A and look at it in terms of information. Let's say we change some information about this particle. It will reflect immediately, near immediately, in particle B. And here's the real kicker. It seemingly does this faster than the speed of light. If, for example, we were to imagine that this information would have to travel in the most direct, efficient space-time line distance from particle A to particle B, right? Well, in order for that information to travel from here to here in near instantaneous time, because they've tested this stuff at distances, the information would have to move faster than the speed of light to get from here to here instantly. So that's why they call it spooky action at a distance, is why Einstein called it that, because it appears like this information that is transmitted from one to another, or energy, is quite literally moving faster than the speed of light, which so far, even Einstein says, this is the speed limit of the universe. You don't go faster than this. Now that's assuming it's moving in our linear space-time from here to here. Now maybe there's other dimensions it's going through where in our space-time reality, it's no distance at all, because somehow it's going into a different dimension or a higher level of reality that we have no scientific bearing for. We just don't know. We just know that it works, and we've observed that we're able to entangle particles and then send information back and forth. But yeah, so I mean, quantum physics, like I said, is absolutely crazy. But for our purposes, this is where, when I say science, quantum physics has told us that as observers, as perceivers, merely by the act of perceiving something, we are changing it. And it happens in the quantum level. By observing the waveform, we force it to collapse to a particle. And vice versa. If we observe it as a wave, it stays a wave. And the name of the book by Amit is that the self-aware universe, how consciousness creates the material world, how consciousness is the creating force in this world, in this universe. It makes everything, you know? So I highly recommend checking out this book. I'll leave a link in the description below. It's fascinating. I'm not done it yet. I think I'm like halfway through. But I just wanted to give you guys some basics. And quantum physics, like I said, is a fascinating topic. And I like this guy's book because he breaks down, in the first couple of chapters, he breaks down classical physics, he breaks down quantum physics, and he breaks down how most of the general scientific community just kind of sweeps quantum physics under the rug because of how many paradoxes it creates. It would force them to completely rethink the fundamental nature of reality. And even today, a lot of scientists aren't ready for that. They're still clinging to that. Same with archaeologists, how archaeologists are clinging to their idea of how history went without realizing that it's great if history is different than the way we think it is. You know, it's great if maybe the ancient alien theory is correct. You know, maybe there was, and even if you don't want to go that far with it, maybe just to believe that humans have been here for longer than we think. And maybe to believe and understand that maybe some humans had more advanced technology. You know what archaeologists do right now? If they find something in an area, and they know this area is supposed to be 500 BC, for example, and if they find something that by all accounts was there at 500 BC, absolutely for sure, proven, it was in the strata at the right level, you know, things like that. But if it suggests advanced technology that didn't exist at that time, instead of the archaeologists saying, wow, we should think about this differently, they go, oh, no, this must be some sort of error, and they call it an UPA. And an UPA stands for an out-of-place artifact. Even though it's in the right strata, even though it's in the right place, even though it's clearly obvious there's no way for this to have been planted here in the future to that relative time. It's clearly from this time era because it doesn't fit with their narrative of how humans evolved and what is right in history. Instead of expanding their own perception, they just sweep it under the rug. And there's tens of thousands of UPAs, out-of-place artifacts all over the place. And some of them are way more damning and convincing than others. So and again, we see the same thing here where it's like human beings get so attached. And this is why we have to also let go in our own lives. We can't be too attached to our understanding of reality. We have to allow it to shift and change and morph. We can't be attached to who we thought we were yesterday. Let's stay open, open to the possibilities. There are so many neat things out here, and if we're so stuck being dogmatic and fundamentalist, even when it comes to our sciences, then we're never going to evolve, or if we do, it's going to be so slow because we're dragging all the older, people stuck in their heads about physics and about archaeology into the future. So it's my little side tangent there. But in any case, that's the basics of quantum physics. If you found this interesting, again, check out the book. You can Google it. If you start Googling it, it's going to get heavy real quick. But I just think this stuff is fascinating. And if you want to see more material like this, let me know in the comments below, and we can dig into even more like quantum physics stuff. I just find this all fascinating. And part of this channel is I share what Spirit tells me to share. And Spirit, I had no intention of making this video this morning. I'm in the midst of doing the meditation series. But I felt called to do it today. So in my meditation, it was like, do a quantum physics video. And I was like, okay. So anyway, I'll see you guys next time. I hope you choose to make it a great day. Peace.